James Webb Space Telescope just revealed how supermassive black holes manage to grow so incomprehensibly large, and the feeding mechanism it uncovered operates on a scale and through a process that no previous telescope had ever been able to directly observe in this detail. Supermassive black holes sit at the center of almost every large galaxy in the observable universe. The one at the center of our own Milky Way, designated Sagittarius A star, contains a mass approximately 4 million times greater than our Sun. The largest supermassive black holes ever measured contain masses exceeding 40 billion solar masses. How objects that begin as stellar mass black holes, formed when individual massive stars collapse, grow into these incomprehensible gravitational monsters has been one of the central unsolved problems in astrophysics for decades. The timeline is the problem. The universe is only 13.8 billion years old, and yet billion solar mass black holes already existed when the universe was less than a billion years old. Growing that fast requires a feeding rate that challenges every model scientists have developed to describe the process. What Webb has now provided is direct observational evidence of how this feeding actually works at the galactic scale, and the mechanism is more violent, more interconnected with the galaxy's own evolution, and more visually dramatic than previous theoretical models predicted. The feeding process begins with what astronomers call an accretion disk. When gas and dust fall toward a supermassive black hole, they do not fall straight in. Angular momentum, the same rotational physics that keeps planets in orbit, causes the infalling material to form a flattened, rapidly rotating disk around the black hole. As material in this disk spirals inward, friction between adjacent layers of gas moving at different velocities generates extraordinary heat. The inner regions of an accretion disk around a supermassive black hole can reach temperatures of millions of degrees, hotter than the surface of any star. This superheated material radiates across the entire electromagnetic spectrum, from radio waves through visible light to X-rays, making active black holes among the most luminous objects in the universe. Webb's contribution to understanding this process comes from its ability to observe the feeding mechanism in infrared wavelengths that penetrate the thick clouds of dust surrounding active galactic nuclei, the regions immediately around actively feeding black holes. Previous telescopes operating primarily in visible light were effectively blind to the most active phases of black hole growth because those phases occur inside the densest, most dust-obscured environments in the galaxy. Webb sees through the dust as if it were nearly transparent, revealing the structure, temperature, and chemistry of material being consumed at a level of detail that has never been accessible before. Webb's observations have revealed that supermassive black holes do not feed at a constant rate. Instead, the feeding is episodic and self-regulating through a mechanism called AGN feedback, active galactic nucleus feedback. When a black hole is consuming material particularly rapidly, the energy released by the accretion disk drives powerful outflows of gas and radiation that push surrounding material away from the black hole. These outflows, sometimes called quasar winds, travel at velocities of thousands of kilometers per second and can sweep gas out of the central regions of the entire galaxy. By removing the raw material that would otherwise continue feeding the black hole, these outflows effectively throttle the feeding rate, creating a natural regulatory cycle. Webb has directly imaged these outflows in galaxies where previous telescopes could only infer their existence from indirect evidence. By mapping the velocity, temperature, and chemical composition of the outflowing gas using spectroscopy, Webb is revealing how these feedback mechanisms interact with the broader galaxy environment, determining where new stars form, how quickly the galaxy evolves, and whether the conditions for planetary systems and potentially life can develop in regions affected by the black hole's energy output. The connection between black hole feeding and star formation throughout the host galaxy is one of the most profound relationships Webb is helping scientists understand. When AGN feedback drives gas out of the galaxy's central regions, it can compress gas in surrounding areas and trigger bursts of new star formation in the compressed regions. Simultaneously, the most intense feedback episodes can heat gas across the entire galaxy to temperatures where it cannot cool and collapse into new stars, effectively shutting down star formation galaxy-wide. The same black hole feeding event that creates the universe's most luminous energy source simultaneously shapes the stellar population of an entire galaxy containing hundreds of billions of stars. Webb has been observing galaxies at various stages of this feeding and feedback cycle, effectively building a library of observations that spans different epochs of cosmic history. By comparing actively feeding black holes observed at high redshift, meaning the universe was younger when that light was emitted, with less active systems in the nearby universe, Webb is assembling the observational evidence needed to reconstruct the complete history of how supermassive black holes grew from stellar mass seeds into the cosmic giants that anchor every large galaxy today. The most surprising aspect of what Webb has revealed is not the violence of the feeding mechanism, but its intimacy with the galaxy's own life cycle. Black holes do not simply consume their surroundings passively. They interact with their host galaxies through feedback loops that determine how quickly the galaxy forms stars, how efficiently it uses its gas reserves, and ultimately, what kind of galaxy it becomes over billions of years. The supermassive black hole at the center of the Milky Way and the galaxy it inhabits did not develop independently. They grew together, each shaping the other's evolution through a relationship that Webb is now revealing in unprecedented observational detail. So here is the question that should shift how you think about the galaxy you live inside. If the supermassive black hole at the center of the Milky Way and the galaxy surrounding it have been shaping each other's evolution for billions of years through feeding and feedback cycles, and Webb is now revealing those cycles in other galaxies in real-time detail, what does that tell us about how much the existence of life on Earth may ultimately be connected to the feeding history of a black hole 4 million times more massive than our Sun, sitting at the center of our galaxy? Follow this page right now if Webb's discoveries about the universe's most extreme objects genuinely fascinate you, because the revelations coming from this telescope are accelerating, and we cover every major discovery with the depth and clarity it deserves every single week.